Thank you very much for inviting me. Am I really kicking off the whole year?
Yes.
Oh dear. Okay. So I'm going to talk about cubic fourfolds and their Hodge theory, so it has something to do with the year, and their derived categories. Maybe I'll stand down here. So I'm going to describe this analogy between cubic fourfolds and K3 surfaces. In particular, everything about K3 surfaces more or less can be described in terms of their cohomology. So their Torelli, the periods, defamation theory, their derived categories. There's a derived Torelli theorem due to Daniel and his collaborators. And I'm going to discuss, so more or less the same is true for cubic fourfolds. Everything's determined by their cohomology. And the analogy with K3 surfaces is pretty strong, as I'll explain. And it can be made precise, and it's much stronger for special cubic fourfolds. And their cohomology really looks like the cohomology of a K3, as I'll explain. And so there's this notion of a special cubic fourfold due to Hassett. And he works out exactly which ones are special. So exactly which cubic fourfolds look to the level of Hodge theory exactly like a projective K3 surface. And then Kuznetsov has this notion of which cubic fourfolds, so that part of their derived category looks like the derived category of K3, and he has this notion of when the derived category is exactly that of a K3. And more or less, the idea of the talk is to prove that these two conditions are the same. So it's to discover is to describe which cubic fourfolds satisfy Kuznetsov condition. That's more or less what we're going to do. And conjecturally, part of the interest in this is that both conditions are equivalent to the cubic fourfold being rational, being birational to P4. But I won't really have anything to say about that, except when I describe all of this through examples, you'll see the rationality in all the examples. Okay. So the notation, X is always going to be a smooth cubic fourfold. It's got a 20-dimensional moduli space. The Hodge diamond looks like this. And if you take out all the trivial pieces coming from P5, you get the primitive cohomology, which looks like this, which looks very much like H2 of a K3 surface. But the signature is 22. And we have a generator. This 1 here is a generator of the 3-1 cohomology and defines a period point and gives you a Torelli theorem. And it looks very much like, as I said, the cohomology of a K3 surface, but the signature is different. So even after you do a Tate twist to make this weight 2 Hodge structure a weight 4 Hodge structure, the numbers look the same, but the signature becomes 19.3, which is different. And again, there's a Torelli theorem, of course. I copied these accents from Daniel's book, so hopefully they're correct. They're kind of similar, but they can't be the same because of the signature. But they can be they can have a maximal sub-Hodge structure of signature 219 in both cases, which might be the same. And that is the case. So for some K3 surfaces and some cubic fourfolds, there is a natural 219 sub-Hodge structure of H2 for the K3 surface and H4 for the cubic fourfold, which are the same. So that was worked out by Hassett. So let me explain that. So what you need is you need an extra class, and we're going to take the orthogonals. So in the case of a K3, it's obvious you take a polarization, and then you take the primitive cohomology. And in the case of the cubic fourfold, well, we've already passed a primitive cohomology. We need one extra class, and we'll take the orthogonal. All right. So we need to understand the Noether-Lefschetz loci. So these are the loci where you have this extra class. And so there's going to be an integer d in all of this. And here's the story for K3 surfaces. So this is familiar. You have, generically, you don't have any integral classes in H11, at least if you allow analytic K3s. And then this Noether-Lefschetz locus is those K3 surfaces where a class, excuse me, I pressed the wrong button, where a class becomes, so an integral class, I beg your pardon, becomes of type 1,1. And the integer in this case is the degree. Yes. Yes, a primitive class. Yes. And so this Noether Lefschetz locus is a divisor cut out by one equation. So you want that the symplectic form, the holomorphic 2 form on the K3, integrates to 0 against this class. So that's one equation. Okay, and then this Noether Lefschetz locus is some kind of moduli space of polarized K3 surfaces of degree d. So K3 surfaces with a line bundle. And then there's a very similar story for cubic fourfolds. So again, generically, you've always got the hyperplane squared class, but once we remove that and pass the primitive cohomology, generically there are no integral classes in the 2-2 cohomology. And then there's a divisor, a Noether Lefschetz divisor of cubics where there is a special class. So we always call it T. So it's an integral class. Again, it's primitive. We always assume it's primitive. And the integer d in this case is the discriminant of the sublattice generated by of all of H4 generated by the hyperplane squared and T. Okay, and so this is the locus where that class becomes of type 2-2. So there's an extra algebraic class. And again, it's a divisor cut out by the equation that the class is orthogonal to the 3-1 form, the generator of the one-dimensional 3-1 cohomology. Okay, and so this is a moduli space of so-called special cubic fourfolds. So these are cubic fourfolds with an extra class, always called T. And Hassett's theorem, so these two, I beg your pardon, so now I can take the orthogonals to these two. I can take the primitive cohomology on the K3 side, and I can take the orthogonal of T in the primitive cohomology on this side. And now these can be isomorphic. And Hassett worked out precisely when they are. All right, so I take the orthogonal to the two classes. The orthogonal in the K3 case is the primitive cohomology of the K3 surface. And in the cubic case, I take the orthogonal to T in the primitive cohomology. So that's the orthogonal to this lattice. And these can be isometric as Hodge structures. And it's the following. It's when is it? It's precisely when the following condition holds. Okay, and you should just remember this as condition star. You can't possibly remember this, or I can't. So D is supposed to be even, not divisible by 4 or 9, or any prime of this form. Okay, so there's a whole list of numbers. 6 is in brackets. You'll see why in a minute. This corresponds to singular cubic fourfolds. All these correspond to smooth cubic fourfolds. And the integer d is the discriminant on one side and the degree of the line bundle on the other side. Okay, so there's some condition, and this will just be called condition star throughout. And later on, we'll see a much more natural... the problems in this subject all come from trying to use cohomology, and the integral structure on cohomology is really the wrong thing. So we'll see a much more natural way of expressing this in terms of topological K-theory later on. Right, so Hassett produces these K3s. So once he has his special cubic fourfold with discriminant satisfying this condition, he produces the K3 just by Torelli. So he produces the sub-Hodge structure and then uses Torelli to produce a K3. But there's geometric constructions for small d, so I give these examples. So this is the kind of non-example which is singular. So d equals 6 corresponds to cubic fourfolds containing an ordinary double point. And these are indeed rational. There's always this sideline about these guys being rational, which isn't strictly relevant to the talk, but I'll show you. Yeah. Yeah, it's more special than this condition. I'll come to that later on. Yeah. Yeah, their condition, I think that's right. Their condition would imply this condition. Yes, that's right. Okay, so let's do this example because it's very simple. So if a cubic fourfold has an ordinary double point, then you can take the lines through that ordinary double point. That's a P4, and you project to that P4, and you get a birational map. It's the usual proof that a nodal cubic curve is rational. You get a birational map from X to P4. So you take your line through the ordinary double point, that intersects the cubic in 2 points, but it's a cubic's degree 3, so it has to intersect in one more point, and that gives you a birational map from Q to pi of Q, so from X to P4. Okay. So this gives an isomorphism from the blow-up of X in the ordinary double point to P4. Sorry, it gives you a morphism. And what does that morphism do? It's generically an isomorphism, but over a K3 surface in P4, it's a P1 bundle. So this K3 surface here is the set of lines that actually lie in the cubic fourfold. So rather than just taking lines in P5, there's the special lines through the ordinary double point, which actually lie entirely in the cubic fourfold. That turns out to be a 2-3 intersection in P4, so it's a K3 surface. All right, so what you end up with is that this cubic fourfold with an ordinary double point, when you blow it up at the ordinary double point, you get the blow up of P4 in a K3 surface. So in this example, that's where the K3 surface comes from. And that gives you a correspondence, and that gives you, it turns out, this embedding of the primitive cohomology of the K3 surface inside the cohomology of the cubic fourfold. And the correspondence later we'll use as a Fourier-Mackay kernel. Then very quickly I'll run over this example because I'm more interested in the next one. So Beauville-Nagi give an example of cubic fourfolds of Pfaffian type. So what do you do here? You take a 6-dimensional vector space, and then you take 2 forms on it. That's a 14-dimensional vector space. And then you take the ones which are degenerate, so they have rank, not full rank less than 4 instead of 6. That's a divisor, and it's a cubic divisor because it's where the 2-form cubed is 0. So there's a cubic in P14. So obviously we should intersect it with a P5 to get a cubic fourfold. So we'll do that in a second. And dually to that, instead of taking 2 forms on this 6-dimensional vector space, you can take 2 vectors in this 6-dimensional vector, these bivectors, and that's where the Grassmannian, that's the Plucker embedding of the Grassmannian lies in there. Okay, so there's some duality between this Grassmannian and this Pfaffian, this cubic. And what we do to get a cubic fourfold is we intersect this Pfaffian divisor with a P5. So that gives me a special cubic fourfold. This is a special construction. It doesn't give you all cubic fourfolds. It gives you a divisor of cubic fourfolds. And on the other side, of course, you should take the orthogonal to the P5, which is a P8. And you intersect with the Grassmannian, and that gives you a K3 surface. So again, these are special cubic fourfolds, and they have a K3 surface associated to them. And that construction that I just described gives you a correspondence, and later on a Fourier-Mackay kernel we'll see later. And so this gives you an embedding of the primitive cohomology of the K3 into the 4th cohomology of the cubic. Okay. And then again, these Pfaffian cubics, these special Pfaffian cubics, are also shown to be rational by Beauville-Nagi. But I'm going to skip over that. And the next example, this is the important example I'm going to use the geometry of in the talk. And it's a non-example, so it's not on the list star. But you'll see there's nearly a K3 surface. So these are cubics containing a plane. And so this is d equals 8. The discriminant's 8. The extra class that we've got here is not on the list because 8 wasn't on that list. Okay, now the plane will be P, and then there'll be another plane, which will be P2, which is the set of, I've written this badly, it's the set of P3s in P5 which contain the plane P. So it's the set of P3s in the middle of this. That's a P2 of those P3s. And any such P3 intersects the cubic in a cubic surface, but it contains the plane, so that cubic surface must be a plane union a quadric. So what we have is a P2 family of quadric surfaces. And in fact, what you find is, indeed, this gives you a rational map. So when you blow up the plane, you find that X is indeed a fibration of quadric surfaces over this P2. Okay. So the generic fiber is a P1 times P1 quadric surface, and the singular fibers lie over the discriminant, which turns out to be a sextic in P2, so you can see the K3 coming. All right, so these are special cubics which are quadric fibrations, more or less quadric fibrations over P2. And everyone knows what to do with a quadric fibration. There's naturally a double cover. So what we do is we take the moduli space of lines in the quadric surface fibers and the moduli space of rulings. So, you know, this, I'm sure most people are familiar with this. So the generic fiber looks like this. So what's the moduli space of lines in this fiber? There's a P1 of horizontal lines and a P1 of vertical lines. Okay. So this is one ruling and this is the other ruling. So S, there's a corresponding double cover. So this is the fiber. This is the fiber of M, the moduli space of lines in the fibers. And this is S. So S is going to, so for each fiber you're going to get 2 points for S, 2 P1s for M, and this is what the original fiber looks like. Okay, so as we run over the base P2, S will be a double cover, and M will be a P1 bundle over the double cover. And it will branch. So over a generic point, you have this quadric here, P1 times P1. But over the sextic, you get the cone over a, I don't know how you draw this. Over the discriminant locus in P2, you get over the sextic curve, you get the singular quadric surface, which only has one family of rulings. And so these 2 points branch, they come together and form 1 point, and that's what gives you this branch double cover, branched over a sextic. Okay, so M is the lines in the fiber. Yeah, so I said all that. And so S turns out, this moduli space of rulings turns out to be a double cover of P2 branched over a sextic curve. So S is a K3 surface. So I've managed to produce a K3 surface, which you might think I shouldn't have done because D is 8. And I have a P1 bundle over it. And that P1 bundle may or may not be the projectivization of a vector bundle. There's a Brouwer class which determines that, which is the obstruction to finding either a vector bundle underlying it or equivalently a line bundle of degree 1 on the P1 fibers, a global line bundle. Okay, so it's obvious. If there's a vector bundle, then there's an O1 line bundle, but equivalently, if there's an O1 line bundle, by pushing it down, you get the dual of a vector bundle. And that's the same as finding a rational section, because its closure defines a divisor, which gives you this line bundle. Okay. So what you find is, indeed D equals 8 is not on this list, and the reason is because generically the Brouwer class is non-zero, and because the Brouwer class is non-zero, it turns out the primitive cohomology of the K3 surface does not embed in that of the cubic fourfold, because there's a 2 knocking about. You have to invert 2. However, it's still a very useful geometry, because sometimes the Brouwer class does vanish. So sometimes there's another class whose integral over the quadric is 1. So it intersects each quadric fiber once, more or less, you should think of. So remember that quadric was h squared minus p. It was the cubic, yes, the p3, the linear section of the cubic minus the plane. So that was this condition here. So anyway, you can ignore that. So if there is this class which intersects each quadric fiber in 1, then by pushing and pulling you end up getting a divisor on the moduli space which it has degree 1 on each fiber. So that's when the Brouwer class vanishes. Sorry, I said that again, the Brouwer class? The Brouwer class is determined by the Hodge structure. I guess I'm more like, I don't know if it's completely determined. I mean, its vanishing is certainly visible in the... Uh-huh. Uh-huh. Class, okay. Then I guess that, yeah. Surely it is, yeah. I didn't know that. Okay, so when we get this extra class with odd integral against h squared minus p, then we find the Brauer class vanishes and the quadric surface bundle has a section. And so you can project, stereographically project in the usual way from this section to a P2 bundle over P2 and find that X is rational. All right, so a simpler example is when you contain two planes. So there you go, there's your extra class, P primed. T primed is P prime. When you contain two planes, then you're birational to the product of two planes in the obvious way. If you take a point in one plane, a point in the other one, take the line between them, that intersects X in a third point. So that gives you the birational map. Okay, but just more generally, when you have this extra class, you become rational. In general, you're not rational. It's thought you're not rational, but it's not known. And that's so indeed, D equals 8 is not on the list, and the reason for that is the guys which are on the list, it's not because of the extra class P. That extra class of the plane does not put you on the list. It doesn't make you rational. It gives you a K3 surface, but a K3 surface with a Brauer class, which you should think of as some kind of non-commutative K3 surface. But what's putting you on the list in this case is this extra class T primed. And that's what's making the Brauer class vanish. So you really have a K3 surface and you're really rational. Okay? So when D equals 8, but there's another D, that should really say D primed is in star. What's going on is the following. So D equals 8 and the Brauer class vanishes. That's equivalent to the existence of this other class, and it's this other class which has discriminant D satisfying, which is on that list. 8 is not on the list, so the discriminant of P is not on the list, but this T primed might be. Okay, so when X is in the intersection of two Noether Lefschetz loci, the degree discriminant 8, 1, this is because it contains a plane, and discriminant D because of this extra class T primed, then that's when you can be rational and you can have a K3 surface associated. Okay, so we prove on the way we needed the following. Actually, what you find is that all of these NLDs, where D lie on Hassett's list, they all intersect this NL8. So you should think of the picture as being something like this. So this is some kind of moduli space of cubics. At the boundary, there's this NL6. That was the one with ordinary double points. And these are all the other ones, NL14, 26. These are all the ones on Hassett's list. And they all intersect this NL8. Okay? And NL8 is not on the list, so these guys generically don't have a K3, or they have a K3 with a Brauer class. And they're not rational. But when they intersect, they get an extra class, and then they become rational and they have a K3 surface. They conjecturally become rational, and they do have a K3 surface in the sense of Hassett. And indeed, Hassett proves that. We really now have that the primitive cohomology of the K3 surface is contained.
So it's not true that any two of these Noether Lefschetz loci intersect?
Yeah, it probably is, yeah. Yeah, the picture's not very...
So is Hassett condition the same as saying that the variety of lines on the cubic is birational to a moduli space of sheaves on a K3?
Excellent. Yes, yes. We'll come back to that, but yes, that's exactly correct. It's birational to a moduli space of sheaves on the K3. Do you know? No, I think... Yeah, that might be known now due to work of Bayer and McCree. I think it's more obvious that Kuznetsov's condition, which I'm going to do in a second, gives that. But I would have to think about it. But more or less, that's what you should be thinking. Absolutely. Okay, so let me briefly say what this rationality conjecture is. I keep saying it. So Harris and Hassett, they didn't actually ever conjecture it. And it's probably a good thing, because probably it's not true. But they asked whether maybe... if your cubic fourfold has a K3 surface in the sense of Hodge theory that we've been discussing, so it has one of these guys is embedded in it, then is that equivalent to x being rational? And the rough idea is sort of clear. If x should be birational to P4, if and only if, well, somewhere you're going to have to blow up a surface in this, and that'll give you a correspondence to some surface, and if you look at the cohomology, it's probably going to be a K3 surface. Okay. So the idea of Kuznetsov's sort of categorification of all this is that instead of using correspondences, you should use Fourier-Mackay kernels. So here's Kuznetsov's approach. So Kuznetsov starts, if you know Kuznetsov, you won't be surprised, he starts with a semi-orthogonal decomposition, or an exceptional collection. So he starts with these three line bundles. They form an exceptional collection on a cubic fourfold. And he takes their orthogonal, so they're right orthogonal, and this is called AX. Okay, so there's sort of this is an admissible, you could do this with any category, but you wouldn't get anything sensible. But this is something called an admissible subcategory because there's a projection back, there's an adjoint to this inclusion. So by just the Gram-Schmidt process. So because these are exceptional, they're like an orthonormal collection. If you have any object in dx, you can make it orthogonal to each of these by, dotting it. So you take your object E, you dot it with one of these OIs, and you remove that piece. And that gives you some object which is orthogonal to OI. And you do that 3 times, and you end up in here. Okay, so this is so-called admissible subcategory. There's a projection, an adjoint to the inclusion. And this category, Kuznetsov noticed, incredibly, is really a K3 category. So it's a non-commutative K3 surface in the sense of Kuznetsov. So it's two-dimensional Calabi-Yau category. It has Serre duality like a K3 would. It has the same size Hochschild homology and cohomology as a K3. And it's actually a deformation of a K3, as we'll see. But in general, it can't be the derived category of a K3 because in particular, it doesn't have any classes in generically, it won't have any classes which are orthogonal to themselves. And if it was a K3, the structure sheaf of a point is orthogonal to itself in the sense of the Euler characteristic of the Homs and the X's from the point to itself would be 0. So non-commutative K3, there's some kind of role for it in mirror symmetry. The mirror of a cubic fourfold indeed is an LG model with a singular K3 in its singular locus. This is all in grey. You're not supposed to take this too seriously. Yeah, we'll see that because we're going to see cases where it is a K3. It is the derived category of a K3, and then all other cases are deformations because the moduli of cubic fourfolds is irreducible. In which sense? So Kuznetsov has a sense of how you should deform categories using A-infinity categories. Yeah, let's not go into that now. I mean, it is a sense it's a sense in deformation theory where you can lose objects. The category can get smaller. So you allow these objects which are curved, which don't have d squared equals 0 and so forth. Anyway, in some sense, okay, so this also explains this remarkable thing that Beauville and Nagi found, that the Fano variety of lines in X is holomorphic symplectic. So it's really a moduli space in this K3 surface, this non-commutative K3 surface, or in this category. And why is that? Because you take your line and you take the ideal sheaf of the line, that's a sheaf, you project it back into this category in the way I said on the last slide. And so this Fano of lines is really a moduli space of these objects. And these are now objects essentially on a K3 surface, so they have a symplectic structure. Okay, so Kuznetsov conjectures the following. So let's call this crazy category geometric if it's really the derived category of a K3 surface. And then Kuznetsov conjectures that X should be rational if and only if AX is geometric. So Kuznetsov was braver than Hassett. He really did conjecture this. And the intuition's the same as before. You're going to have to blow up a K3 surface somewhere. And Kuznetsov went through the known rational cubics, which are essentially the examples I've just done. And he proved that indeed the derived category of S of a K3 surface embeds in the derived category of the cubic fourfold in every case. Essentially, I've shown you how to do that, more or less. I showed you all the correspondences, and those can be lifted to Fourier-Mackay kernels. Although, yeah, there's this caveat, no one's ever shown a cubic fourfold is irrational. I don't know the status of this. Do you know the status of this? Oh, oh, I should remove this. Can you scratch this from the video? Sorry, John Lee. Okay, so we still don't know we don't know a single example of a cubic fourfold which is irrational. Right, so what I'm going to try and do, the point of this talk, is to show that Kuznetsov's condition, so this AX being geometric, being the derived category of K3, should be entirely cohomological. It should be the same as Hassett's condition. And so how am I going to do that? I'm going to start, you remember that picture? I'm going to start on this locus here, which we understand very well. I'll explain it. I've explained this locus. This is the quadric fibration locus, NL8. We understand the geometry very well here, and I'll explain it in terms of derived categories in a second. And then I'm going to start, because that intersects all of these loci, I'm going to start deforming down these loci, starting on NL8, or its intersection with one of these loci. So, you know, Kuznetsov kind of understands this locus, and, yeah, these two loci, and this locus, NL8, 14, and 6. And we're going to try and understand all the others, 26, 38, and so forth, by defamation theory. So I'm going to start on their intersection with NL8, and then I'm going to deform.
So wait, so you're saying if AX is geometric, just by looking at cohomology, it has to be containing one of these interselections?
Yeah, because if AX is geometric, then it has this, the structure sheaf of a point in the derived category of the K3 is going to exist in this AX. And so that gives you a class in cohomology, and that will be enough, actually, to show. So it's Hassett. It is of Hassett type. Yeah.
So you want to prove conversely that.
So I want to prove that. That's the easy direction, and then I want to prove the converse, which we don't quite succeed in, but you'll see. So we prove that generically on a Zariski open. Okay, so I want to go back to these quadric fibrations again. And this is the geometry we're going to use. So remember what we had. We had X was essentially quadric fibered by quadric surfaces, and we got this. That gave us this double cover. Now, a point in this double cover, that gives you a choice of ruling. You choose one of the lines in the ruling, either a horizontal line or a vertical one, generically, and take the ideal sheaf of that. So you can see it doesn't matter which one I take, because it's a divisor. So it's either O minus 1, 0, or it's O, 0, minus 1, generically. And I push it forward to X, and I consider S as a moduli space of these objects. And precisely because I made a choice here, because I had to choose one of the lines, it's not clear there'll be a universal sheaf. And of course there isn't because of this damn Brauer class. Okay, so S is a moduli space of these objects. And there's a universal object, but only after you twist by this Brauer class. Okay, so there's not a universal sheaf, there's a universal twisted sheaf. And Kuznetsov proved some time ago that you could use this as a Fourier-Mackay kernel to give an equivalence between the twisted derived category of the K3 surface and this AX. All right, so all along this locus, NL8, we understand things perfectly. This dx contains the derived category, not quite of a K3 surface, but a twisted one. And then when we hit any other NLD, where D is on Hassett's list, then we know the Brauer class vanishes, and we really see that X becomes geometric, AX becomes geometric. So we really get the derived category of S being isomorphic to AX whenever we are at the intersection point of NL8 with one of Hassett's NLDs. Okay. So we want to show the two conditions are the same, Hassett and Kuznetsov. So we want to show that when X is in NLD on Hassett's list, AX is geometric and vice versa. Okay, so this is saying, essentially the derived category can be described cohomologically by some derived Torelli theorem. So Mukai and Orloff have and Daniel and so on have theorems like this for K3 surfaces. So we prove this generically. So the theorem is that it's true in one direction and it's true on a Zariski open in the other direction. So the Kuznetsov locus is dense and Zariski open in the Hassett locus. And of course we expect the two loci are equal, but we prove this by defamation theory, and then one would have to specialize or take some closure of this above result. And the problem is that taking limits of Fourier-Mackay kernels is very difficult. You tend to get something kind of, if you had a nice way of taking limits by maybe taking stable sheaves or something with stable complexes, then you'd be fine. Say that again? Yes, of irreducible divisors. In each one. Yes. Yeah, that's right. So each of those Hassett divisors is irreducible divisor, and in each one we get a Zariski open. No, I see what you mean. No, it's Zariski open in each of countably many divisors. That's correct. Okay, so you can't take limits of these Fourier-Mackay kernels in any nice way, but you can take limits of algebraic cycles. So a corollary of this is that this is going to be true over the whole of Hassett's locus, not as a Zariski open. So for instance, we can prove that his Hodge isometry, his Hodge isometry between the primitive cohomology of the K3 surface and the fourth cohomology of the sublocus of the cubic fourfold is induced actually by an algebraic cycle. And we can also prove that more generally any Hodge isometry between the transcendental lattice of a K3 and the transcendental lattice of a cubic fourfold is induced by an algebraic cycle. Okay, essentially because we can prove it for these over these Zariski opens and then take limits. Okay, so how does the proof go? So the first thing we do is we reinterpret that horrible D being in star condition in the following way. So topological K theory turns out to be much, much nicer. In terms of the K theory of this category, this AX category, what we find is the following. D satisfies star if and only if you have two classes satisfying these conditions here. So giving you the A2 lattice. So you have these two integral classes which satisfy these relations. So these look like they're what you have to have if you're going to be the K theory of a K3 surface. Well, it's a line bundle. So on a K3 surface, yeah, sorry, not a line bundle. Yes, line bundle-like, sorry. Yeah, so if you have a K3 surface with a line bundle and a point, then those two classes will satisfy these conditions. And so this proves the easy direction. So if you're Kuznetsov, then you have these classes, A and B, and so you satisfy star. All right, so that's half the paper, but I'm not going to go over that bit. You can imagine it's a big mess in lattice theory. If you like that kind of stuff, you're in the wrong seminar. So conversely, we're going to the idea is the following. So this is the whole idea of the talk. If you're in Hassett's locus, then why on earth should you be Kuznetsov? The reason should be that we now know you have these classes A and B, and what that tells us is you should be able to produce the K3 surface. What's the K3 surface? It's the moduli space of sort of stable objects of class A. Okay, that's the whole idea. So once you have this class A, you should be able to form a moduli space of objects with K theory class A, and that will be a K3 surface if you can do it. And that'll be the K3 surface we're looking for. And then the fact that B is there will just mean that it's a fine moduli space and it has a universal sheaf, and therefore you can use that as the Fourier-Mackay functor and you'll be done. All right, so that's the idea, but of course we don't know how to form moduli of objects in general. So what we do instead is we proceed by defamation theory. So we start with points we understand. So instead of starting with an arbitrary point of NLD, we start with an intersection, a point in the intersection of NLD with this NL8, where we have Kuznetsov's result and we can really understand everything, and then we'll deform. So we first do the thing I said before. We prove the intersection's non-empty. And then the Brouwer class vanishes. So we use Kuznetsov's description now, because we're on NL8. And the Brouwer class vanishes because we've intersected with NLD. Yeah, sorry. Oh, sorry. Yeah, we can't. I mean, that's why we don't. That's what we want to do, is just form a moduli space of objects in this category whose K-theory class is A. But we can't do that because, you know, we don't have a stability condition or something. Right, so we're going to do it at a point here. Here we can do it. We can form such a moduli space. We know how to. Okay, so we choose such a point, and now we have Kuznetsov's description of this AX is some twisted derived category, and the Brouwer class vanishes because we're on this NLD. Okay, so we now we're cooking, we're moving because we have this geometric condition. We really have the derived category of a K3 surface, but this is the wrong equivalence. Okay, because this equivalence is the one that's relevant to NL8. This is the one that Kuznetsov gives you, and that's not what we want. We want the one relevant to NLD, which will deform in the NLD directions. So this equivalence expresses S as a moduli space of objects which deform along NL8, not along NLD. So this is the wrong equivalence. Okay, but we do have something now, because we now can use geometry. In fact, we can use Mukai, because we've really got our AX really looks like the derived category of a K3 surface now. So we have lots and lots of results. In particular, Mukai-Orloff prove that there's now a moduli space of stable objects of class A. Okay, so that's the remarkable thing. So all this work of Mukai and later Orloff on K3 surfaces shows you that in this case, where you're really geometric, you can form a moduli space of stable objects of class A. And under mild conditions, there'll be a moduli space of vector bundles, in fact. Okay, and it's got dimension 2, it's holomorphic symplectic, it's compact, and it's a fine moduli space because of the existence of this class B. So you really get a K3 surface and a universal object. So now you get an equivalence to a different K3 surface, and when you compose these equivalences, so the new K3 surface back to the old one and then back to AX, that's now the correct guy, which stands a chance of deforming. Okay, so we now have M is now a moduli space of objects of type A instead of some other crazy type to do with the quadric vibration. Okay, and this is the guy which ought to deform along NLD. Is that okay? All right, so we're sat at one of these intersection points, and now we're going to deform along NLD. So finally, we're going to deform into NLD. Deform M with it, that bit's easy because we have Torelli. All right, so as we deform X, we have this class of discriminant D. We take its orthogonal. We get some abstract Hodge structure by Torelli and Hassett's result. It is the cohomology of a K3, and so everything works fine. Okay, so we can actually deform the K3 surface M with it. And the hard bit, all the work in the paper goes into showing that the Fourier-Mackay kernel deforms with it. Okay, so we've managed to produce the right X with the right class, the right equivalence, the right K3 surface, and as we deform, we can deform the K3 along, and what we need to show is we can deform this equivalence along. We can deform the Fourier-Mackay kernel. And that'll prove everything, because these NLDs are all irreducible. So if it deforms to all orders, then it deforms to as a risky open. And once the kernel deforms, the fact that the kernel defines a full and faithful embedding is also an open condition, as a risky open condition. So this will be enough. So the work goes into showing that this This kernel here deforms to all orders. So all we've done so far, what I should say is we've managed to find, as we move down this locus, we've managed to find a K3 surface that goes with us and a class which always remains of the correct Hodge type. It remains PP. Okay, so that's what we've done. Is we've just done cohomology and lattice theory so far. So we found the class, we found the K3 surface, we've got the equivalence at this point, and as we move off this point, what we've arranged is that that class will remain PP. So the obvious obstruction to this Fourier-Mackay kernel deforming is not there. The cohomological obstruction is not there. So cohomologically, there's no obstruction to deforming this kernel. That's what we've arranged. And then we want to show that that means the kernel actually deforms. So the obstruction to deforming the kernel should be entirely cohomological. All right, and that's this last thing. So this is defamation theory. So firstly, there's this marvelous T1 lifting theorem of Ran, Kawamata, and Deligny, which says that more or less you can reduce to first-order defamation theory. So you take your K3 and your cubic, so long as you can deform over spec of the dual numbers, that's not quite enough. But so long as whenever you take your K3 and your cubic over some Artinian ring, and then that construction you times by spec of the dual numbers, more or less, if you can do that kind of first-order defamation theory, then you can do arbitrary defamation theory. So you only need to show that this kernel deforms, so this kernel, not just on the K3 times the cubic, but on a family of K3 times cubic over some Artinian ring. If you can show that guy deforms to first order, then you're done. It deforms to all orders. Okay, so but more or less, I'll forget about the Artinian ring. I'll just talk about the first order defamation theory. But it's not much harder to get everything else. So to do that, we refine some ideas of Toda and Hoybrush, Macri, and Stellari. And the idea is the following. So, so why should the obstructions to deforming this kernel be entirely cohomological? It's for the following reason, which is one of these things that makes K3 so incredible. What you do is you start off with your moduli space. This was a K3, remember, and your Fourier-Mackay kernel, and that gives you an equivalence from the derived category of this K3 surface to this AX. And so I'm going to pretend they're the same because I have an equivalence. So when I pretend they're the same using this equivalence, then what do I have? I just have dm is by the identity isomorphic to dm sat inside dx. All right. Let me try and write this up. So what do I have? I have sort of dm is sat in, well, it goes by the identity to dm, which is sat inside dx. This is really ax sat inside dx. And what I want to do is I'm going to deform x and m. So I'm going to deform dm and dx. So, well, as I deform dx, ax always exists. Kuznetsov told us how to define it as orthogonal to those three triangles. So as I deform m and x, I get a deformation of this guy and this guy. Okay? So if you ignore the fact that they're the same, what I'm going to do is I'm going to deform this guy, and I'm going to deform this guy. Not necessarily in the same way. All right? So I'm going to deform this guy and this guy, and I want to know, does the identity Fourier-Mackay deform as I deform this guy and I deform this guy? Okay. So the identity is just represented by the Fourier-Mackay kernel, which is the structure sheaf of the diagonal. And I want to know, does the diagonal deform? Well, you won't be surprised at what the answer is. So I have, essentially, I'm going to deform m and this m. I'm slightly deceiving you. I mean, this m, I'm not going to deform it as a variety. I'm going to deform the category, dm. Okay. So I'm going to deform. In this Kuznetsov sense. So I deform it as an A infinity category, and so then I have these curved objects whose square might not where d squared isn't 0, and then I throw those away. Does that?
So in particular, when you speak of morphism, it is automatically given by a given.
Yes. So that's a result of Orloff, that I think, that any full and faithful, or Bondal and Orloff, any full and faithful functor is represented by a Fourier-Mackay kernel. So, I mean, we can be much more concrete. I'm going to deform this K3 surface. So I'm just going to, by the deformation of this category, I just mean the derived category of the deformation of the K3 surface. So I can be concrete on this side. On this side, I can be concrete because I'm going to deform the cubic fourfold. And so I get this category here as the orthogonal to 001 and 02. So I could be more concrete. Okay, so I'm going to deform this guy, and I'm going to deform this guy. So I'll put a T there. And I want to know, can I deform the Fourier-Mackay, the equivalence between the two? Right? So let's just pretend, well, what do I start with at t equals 0? All I have is the structure sheaf of the diagonal on m0 times m0. And now I'm going to deform this guy, and I'm going to deform this in some non-commutative direction. And I want to know, will this deform with it? Okay, so where does the obstruction live? It lives in here. All right, and then we have this HKR isomorphism. So this is what? H0 of x2. So the spectral sequence collapses. Okay, this is, you can compute very easily. This is H0 of wedge 2t plus t of m, H1 of t of m plus H2 of O of m. All right? So this is the obstruction to deforming this guy. And the obstruction is essentially telling you whether or not these are remaining isomorphic. So in other words, it's telling you whether or not this is deforming compared to this one or not. And these are indeed the deformations of the derived category. Those are the commutative ones where I just deform the complex structure on M. These are the ones where I deform that twisting class, that Brouwer class. And these are some Poisson non-commutative deformations. All right? But the point is, because I'm on a K3 surface, this is entirely cohomological. So using the symplectic form, this becomes H02, H11, and H20. All right? So what do I say here? So that's this condition here, that the obstruction lies in essentially cohomology. So you can precisely identify it. You can identify what this obstruction is. And it's the Kodaira-Spencer class of M minus the Kodaira-Spencer class, essentially of X. So the Kodaira-Spencer class of M lies in here. And the one of X, you have to project back to the category and relate it back to here, but it essentially lies in the same space.
Why do you do this in the language of categories and not with algebraic cycles and deforming the T3?
Because these are much better than algebraic cycles. Because the cycle might be hideously singular. And so the deformation theory would be awful. But here you have this categorical thing. The fact it's an equivalence tells you that you understand this. You understand this. So what this says is, I did some identification to get here, but in general what you have is you have some universal sheaf on the product. And what this categorical nonsense tells you is that you understand this in terms of cohomology. You don't understand this for an algebraic cycle. This will be some very complicated thing. But this categorical, the fact that it gives you an equivalence of categories tells you you have complete control over this. So it's much simpler. Even though, of course, you're right in the sense that if the Fourier-Mackay kernel was the structure sheaf of some...
The situation is that you have the deformed T3 and you have the deformed the correspondence between the T3 and the T3.
Mhm.
You want to put that exponent derived.
Yes.
And you do this via this category argument.
So from your point of view, that is what we do, yeah, because you care about the cycles. From my point of view, I actually care about the equivalence of categories. So I start with, I really want to deform the Fourier-Mackay. So if the Fourier-Mackay kernel is the structure sheaf of a nice, smooth algebraic cycle, then you're absolutely right. You could do the defamation theory there, and you would see the same picture, but it might be something hideously singular. And you know, if this was K3 surfaces rather than cubic fourfolds, and that cycle was really smooth, this would reduce to your theorem about deformations of Lagrangians. But this is like a derived version. It's very similar though. It's the same idea.
So you could express it in terms of this x2, the kernel with itself, in something that is small enough to be seen geometrically.
Yeah, so this x2 from the kernel to itself is actually isomorphic to this, as I was explaining. So it lies here. So you can identify what this obstruction is in this group, and it turns out to be just this. So it's just the difference in the two Kodaira-Spencer classes where I've identified the Kodaira-Spencer class of X. I've taken it cohomologically, so I've used the period point to turn it into a cohomology class in the usual way, and then I've projected that to the K3 part of the cohomology. But anyway, I mean, under some natural identifications. So anyway, this is 0 when these two match up, which is just under the identifications I've made. That's just the condition that when I deform X, M takes the appropriate deformation. The period points deform together. They continue to match up under Hassett's equivalence. Okay, so because I precisely defined M by Torelli to satisfy that this is 0, so that M and X are cohomologically the same as I deform, then this obstruction is always 0, and so I can always deform. Okay, any questions about that? So I've got just one last slide to say that I completely misled you. So this rationality thing, this is what we were talking about before. Right, so this is Kieran's question. So Kuznetsov's conjecture basically says that X should be rational if and only if the Fano of lines on X is birational to a moduli space of sheaves on a K3 surface. That's what Kuznetsov's conjecture more or less says. And Galkin and Schender seem to show, but there's modular conjecture about some motives, which we don't know if it's true or not. But their work very strongly suggests that actually X should be rational if and only if this Fano of lines is birational to a Hilbert scheme of points on a K3. All right? So that seems more natural to me, actually. I mean, this is really about geometry. Rationality probably shouldn't be anything to do with derived categories. Mm-hmm. Yeah, but it would be extraordinary. Suppose that was wrong. It would still be extraordinary that they end up with, you know, they end up with an expression in the Grothendieck group of something times by basically fx minus Hilb2 of a K3 surface. You know, in K0 var, they end up with something like fx minus Hilb2 of a K3 surface times by something. And okay, so they don't know if it's a 0 divisor and they can cancel. But nonetheless, the fact that that equals 0, the fact that they know that quantity equals 0, it would be remarkable if that quantity equals 0 because there's something, because it was a 0 divisor. It's absolutely remarkable. Yes. Yes. Yeah, I agree. But still, we know many cases where this is true already. So we know many cases where fx minus Hilb2 of a K3 is 0 in K0 var. And they show it's always 0 after multiplying by something, more or less. It would be remarkable if and only if it's rational. I beg your pardon. It would be remarkable if... Well, okay, so maybe the condition is it's rational if and only if fx minus Hilb2 of a K3 is a 0 divisor. I don't know. But still, that would be very hard to interpret that geometrically. Anyway, I quite like... I prefer this conjecture. I think we should throw away this previous conjecture and work with this. I don't know. And, you know, there's a Hassett... and Nick Addington worked out a Hassett cohomological criterion for this as well. For this fx being birational to a Hilb2 K3. And it's this stronger condition, star star. So star star implies star, but not the other way around. All right? So in particular, derived categories got nothing to do with rationality, probably. Okay. Sorry for wasting your time.